So this is the supplemental problem session video lecture for the Chapter 5 materials for MAP 4113. I just want to go over a few odds and ends and examples here in this video. So first of all, I want to highlight a formula that kind of breezes by you when you're reading the book. It's just a part of a proof, and I think it might be the proof of the memoryless property. But there's a little lemma, I don't know if it's called a lemma in the book, but it says this. If y is a random variable with the probability that y is bigger than or equal to 0 is equal to 1, so it's a non-negative random variable, then the expected value of y can be calculated as the integral from 0 to infinity of the probability that y is greater than little y dy. And this is in fact a very powerful result and something that you can use in a lot of different situations. And in fact, what I want to highlight at first is that this is true for any random variable at all. It doesn't have to be continuous. It doesn't even have to be one of the random variables, one of the kinds of random variables that we talk about in this class. Any random variable at all, this is going to be true. As long as it's non-negative, then this formula is valid. For example, if y is discrete, then the integrand here is a step function, and so the integral just turns into a sum. So I want to show also the proof of this thing, or proof sketch, because I think it's kind of, I don't know, enlightening a little bit and gives you a little practice with some Calc 3 stuff that's going to be coming up later. So let's start to do this proof. Let's start on the right-hand side. And this is not going to be a general proof for any random variable. We're going to assume in the proof that y is a continuous random variable, so it has a density. Okay, but this result doesn't need that. Just the proof I'm showing you needs it. There's a different proof that works for any random variable, but I can't show that to you. That's beyond the scope of our class. But here, so if y is continuous, then that probability inside can be written as an integral. It would be the integral from y to infinity of the density of capital Y. Let's say we put a t here, t, dt. So that's the probability that capital Y is greater than y. And then we need to integrate that dy. All right. So now if I get rid of those parentheses, then I just have a double integral. dt dy. And let's look at that region over which we are integrating. And let me plot it here. We'll say in a yt plane. So I'm integrating, y is going from 0 to infinity. And for any particular value of y, pick a little value of y, then t is going to go from t equals y, so here's the line t equals y, up to t equals infinity. And for all the different values of y, t will go from t equals y to t equals infinity. So there's the region that I'm integrating over. So if I want to reverse the order of integration, I want to go dy dt, and I want to look at that graph or that picture that I've just drawn and think about how to reverse the order of integration. So now t is on the outside, so I have to look what are the possible t values. Well, t can go from the origin here all the way up to infinity, so t is going from 0 to infinity. And for a particular t value, what is y going to do? Y is going to, I have a tablet here. I can experiment with colors. Okay, so t is going to, for a particular t value, y is going to go along this red line segment that I'm making. Okay. And so it's going to go from y equals 0. I'm going to change back to black. Wait, where's black? Oh, there it is. So y is going to go from y equals 0 up to this point right here, which is y equals what? Well, solve this thing for y. It's y equals t. So y goes from 0 to t. Okay. It's a little bit difficult to do these lectures without being able to point at things. But I'll do my best. Okay, so in the inner integral, that integrand has no little y in it. It's just a constant, so we can pull that out, and the inner integral just becomes t times f sub y of t dt. And now we have to remember that y is a non-negative random variable, so its density is 0 on the negative half line. So this is actually equal to the integral from negative infinity to infinity. And that's because, well, how should I say it? Because capital Y is greater than or equal to 0. So f sub y of t equals 0 for all t negative. And then when you look at that, well, you should recognize that that's the formula for the expected value of y. Okay. So that was one thing I wanted to highlight. If I come back, what did we just prove? This formula right here. And as I said, so I showed you a proof that gives you some practice with Calc 3, changing order of integration, but that proof only works for y that are y when it's a continuous random variable, but that formula is true for any random variable y. All right, the next thing I wanted to highlight was a formula involving variance. So let's say I wanted to know what the variance of ax plus b is. So here x is a random variable, a and b are constants. Okay, well, let's say mu is the expected value of x. Then we've seen before that the expected value of ax plus b is just a mu plus b. Oh, let's try this. There. All right, so remember, if I have a random variable, well, let's give it a name. Let's let y be ax plus b. Then the variance of y, there were a couple of different formulas, right? On the one hand, there was the formula that said that it's the expected value of y squared minus the expected value of y squared. That's one formula that you can use. The other is the definition that says it's the expected value of y minus the expected value of y, whole thing squared. So let's use that second one. And then I can write this as the expected value of ax plus b minus a mu plus b squared which equals the expected value of ax minus a mu squared, which is the expected value of a squared times x minus mu squared. A is not random, so we can pull that out. So I have a squared times the expected value of x minus mu squared. And that is the definition of the variance of x. So in the end, what we've just shown is that the variance of ax plus b is equal to a squared times the variance of x. So when you add a constant to a random variable, that does not change the variance. And if you multiply a random variable by a constant, you have to multiply the variance by that constant squared. Okay, so those are just a couple of things I wanted to highlight. Now I want to do an example. Well, I'm not sure how long this video has been. I didn't set a timer. You know what? I am going to stop the video now and make a part 2. Okay, I'll see you in part 2.